Time domain analysis of feedback control system module 3. Content classification and basic definition, time response of first order system, time response of second order system, error analysis and Routh stability criteria. Order of a system. Consider system defined by a transfer function. This is a generalized transfer function. T of s is equal to C of s divided by R of s, Bm s to the power of m plus Bm minus 1 s to the power of m minus 1 till b naught. In the denominator, an s to the power of n plus an minus 1 s to the power of n minus 1 till a naught. The order of this system is n, which is defined by the highest power of for s in the denominator. So in this example, when you see this, it is s to the power of 0 and here is to the power of 1. So the highest power of characteristic equation is 1. So the order is first order system. In the second example, s square is the highest order, so it is second order system. Similarly, in the third example, you can see the power of s is 4, so it is fourth order system. So to define order of a system, we concentrate on a transfer function. In the transfer function, we concentrate on the characteristic equation, that is the denominator equation, and we'll find the power of s. Whichever has the highest power of s, we consider that as the order of the system. To understand the system type number, it is defined as the number of poles at the origin of the open loop transfer function g of s into h of s, where g of s is the gain, h of s is the feedback. Now generalized g of s into h of s, that is the open loop transfer function, is given by bm s to the power of m plus bm minus 1 s to the power of m minus 1 plus it goes on till b naught. In the denominator, s to the power of c into an s to the power of n plus a n minus 1 s to the power of n minus 1, it goes on till a naught. Now the important part where we will find the system type number is s to the power of c. So in the example, as you can see, g of s h of s, that is the open loop transfer function, is equal to 50 divided by s plus 1 s plus 4. So the denominator is nothing but the characteristic equation. So if I equate it, I get s is equal to minus 1 and s is equal to minus 4. Now for the system to be type 0, what does that mean? Number of poles at the origin. In this case, there are no poles at the origin. Okay, so that's why it is type 0 system. Okay, in the second example of open loop transfer function g of s into h of s, in the numerator we have 0 equations, that is 10 s square plus 3. In the denominator we have characteristic equation. As you can see, if I equate this equation, I know that s square means there are two roots in this. So 1 s1, let's say s1, I get 0. Again I have other root s2 which is equal to 0. So the power of s is nothing but c, that is 2. So that's why, and there are two poles lying in the origin. Okay, that's why the system of type is 2. To understand the time response of a closed loop control system, first thing is we need to understand the definitions of some of the parameters. So first is the time response. The time response of a system is the output response, which is a function of time when input excitation is applied. The time response of a control system consists of two parts. One is the transient response and the other is the steady state response. If I want to define it mathematically, that is the total time response, that is C of t is equal to Ct of t, where this small t indicates the transient response, plus Css of t, and the Css of t indicates the steady state response of the system. Now the transient response is the part of the response which goes to 0 as time increases. Mathematically, limit t tends to infinity, Ct of t will be equal to 0. The transient response may be exponential or oscillatory in nature. This is a very important sentence. The next one is the steady state. The steady state response is a part of the total response after transient has died. That is, when Ct of t is equal to 0, the next time duration is nothing but the steady state response. The steady state error. If the steady state response of the output does not match with the input, then the system has steady state error denoted by ESS. To understand the concept of transient time and steady state response of a system, let us take an example of analog ammeter connected to a simple system. And in that system, it's supposed to show 5 amperes. Let us say that this is the time scale, okay, and this is the amplitude, and this is the current. It has to show the value. Now, with respect to time, it moves something like this. Initially, it oscillates. It oscillates. After a fine duration of time, it becomes stable and it shows the magnitude as 5 ampere. Now, this oscillation is nothing but the transient period. This is nothing but transient period, and this stable steady system, steady value is nothing but the steady state response of the ammeter. And why we get this transient system is because of the friction of the pointer. It will take some finite time to become stable. From the previous slide, as we know, in a system there are two components. One, it exists, the transient exists in either exponential or in oscillatory mode. So this is the first diagram, that is the figure A, shows the exponential, and C of t, that is the total time response, is the sum of transient time plus steady state. Now this exponential rise is nothing but the transient duration, and this is the steady state duration. And the error is that the ESS is nothing but the steady state error. It is the difference between the desired output value and the actual value. The desired output value is this, there is a step input, and the actual value is this one, that is ESS. And whatever the difference is, that is ESS. In the similar way, if you go into the oscillatory mode, the total C of t, that is the total time response, is nothing but the oscillatory transient duration plus the steady state. And again, the error is defined in a similar way. Now, many signals are available which are the function of time and can be used as a reference input for the various control system. And these signals are step, ramp, sawtooth type, square wave, triangle, etc. But while analyzing the system, it is highly impossible to consider each one of it as an input and study the response. Hence, from the analysis point of view, those signals which are most commonly used as a reference signal are known as standard test signals. And in our case, we have the first signal, that is a step function, or we can call it as a position function, and it's given in the figure. So we have v of t uh, with respect to time reference, and k is the amplitude of that signal, that is a step signal amplitude. In step input is nothing but u of t, that is the value is 1, and we are only concentrating when the input is starts from 0 to infinity. So from 0 to infinity, the value will have some magnitude, that is k. From minus infinity to 0, the value will be equivalent to 0. Now, if I apply Laplace transform to this function, that is Laplace transform f of t is equal to 0 to infinity, u of t is the given input function, e power minus st into dt. So u of t is nothing but 1 because it's a step input, and e power minus st dt. If I solve this, I get the answer as 1 by s. Now the second one is the ramp function or the velocity function. The ramp will start from the origin and increases or decreases linearly with respect to time. Let r of t be the ramp function. So r of t is equal to 0, that is t less than 0. If t is greater than 0, it is k into t. K is the magnitude, and k will be greater than 0. So if I apply Laplace transform to this, I know that L of Laplace of r of t is equal to 0 to infinity r of t e power minus st dt. And what is r of t? R of t is nothing but k into t with respect to time. So the final answer I get is k divided by s square. In the previous case for step input we got 1 by s. For a ramp function we are getting k by s square. Now the third signal is parabolic function or acceleration function. The value of r of t is 0 for t less than 0 and is quadratic function of time for t greater than 0. The parabolic function represents a signal that is one order faster than the ramp function. The parabolic function is defined as r of t is equal to 0 for t less than 0. R of t is equal to kt square divided by 2. K is the magnitude. Since it's parabolic, since it is curve, we are getting the function as t square divided by 2. For a unit parabolic function, k will be equivalent to 1. So we get t square by 2. So when we apply Laplace transform to this, I know the Laplace of r of t is equal to 0 to infinity. R of t is the input parabolic test signal e power minus st dt, and r of t is nothing but kt square divided by 2. So what we get at the end, it is k divided by s cube, and this is the parabolic function which is a curve. The next important response is impulse response. Consider figure 1, that is v of t with respect to t. The first pulse has a width t. As you can see, this is the first pulse which has a width t and a height of 1 by t. The area of the pulse will be 1. If we half the duration and double the amplitude, we get the second pulse. That if I move this point to this t by 2 point, the t value is reduced to t by 2 and the amplitude is raised to 2 divided by t, but the area remains the same, that is unity. Now as we go on like this, we get the second waveform, that is at exactly at 0 I have a higher magnitude, okay, and it is represented by delta of t, that is the impulse response with respect to time. So we can say that as the duration of the pulse approaches 0, the amplitude approaches infinity, but area of the pulse is unity. The pulse for which the duration tends to 0 and the amplitude tends to infinity is called impulse. Impulse function is also known as delta function. So mathematically we write that as delta of t is equal to 0, where t is not equal to 0. When t is equal to 0, the impulse output is infinity. Now this is a very important summary of all the test signals. So we have unit step signal that is represented by u of t, and the Laplace transform of it we got 1 by s. Next is unit ramp function, that is symbol is r of t, and we got 1 by s square. For parabolic we can use the same symbol r of t, and the output function is 1 by s cube. For unit impulse delta of t, it is 1. Normally students will get confused with unit impulse and unit step. Unit step is 1 by s and unit impulse is 1. Its area is always 1.